Welcome to Section 7b. We'll be talking about probability, joint probability, independent events, dependent events, and so forth. So, Roman numeral 1, where we're going to be combining probability using and or joint probability. And means times when we're talking about probability. So let's move to rolling 2 dice and both of them getting 4s. We could use the theoretical probability, which we already did previously, which is 1 out of 36. Here are all of the outcomes of rolling 2 dice, and there's only one in here out of the 36 outcomes that would be 2 4s. But we're not always going to find all of the outcomes. We could just talk about the probability of rolling 1 4 and the probability of rolling another 4 using both dice. So with the first dice, rolling 1 4 is 1 out of 6. There's 1 4 out of the 6 sides. And the probability for the second die, again, 1 4 out of 6 sides. So the probability of rolling double 4s is the probability of rolling a 4 times the probability of rolling a 4, which is 1 over 6 times 1 over 6, which equals 1 out of 36. So we have two ways, but this way is going to be faster when we get into larger things. So we don't have to find all of the outcomes. The first thing we're going to talk about are independent events, where one event does not affect the others. So if I roll my one die, it's not going to affect how the other die rolls as well. Those are two independent events. Here's our first example. The probability that a 100-year flood, well, 100 years means 1 out of 100 years, or 0.01, the probability of it striking within a given year will strike a city in 2 consecutive years. So I have the probability that it will occur times the probability that it will occur, just like we did here, or 0.01 times 0.01, which gives us 0.0001, or 1 in 10,000. All right, let's move to the next example, where I'm tossing 3 coins and trying to find the probability that I will get tails, tails, and tails, or 3 tails. So the probability of getting the tails in the first toss, times the probability of getting tails in the second toss, times the probability of getting tails in the third toss. So the first toss, I have 1 out of 2 chances of getting the tails, and the second, the probability of 1 out of 2, and the last one, 1 out of 2, or 1 out of 8, which we also showed in section 7a by listing out all of the possibilities, or all of the outcomes of probabilities. With my 3 coins, I can have heads, 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 tails, tails, heads, heads, tails, and so forth. And we listed them all out. And there was only one possibility, or one of those, out of 8. Let's move to dependent events. This is where one event will affect the other. And to find this, we need to do the probability of A and B. This would be the probability of A times the probability of B after A has occurred. So let's move to something like bingo. There are 75 buttons, 15 for every single letter in the B-I-N-G-O. So I have 15 B's, 15 I's, 15 N's, 15 G's, and 15 O's. What is the probability of drawing 2 B buttons in the first 2 selections? So I pull out a B button and I hang on to it, and then I pull out another B button. So I'm wanting the probability of a B and then a B. So I want the probability of drawing just a B, and then I times it by the probability of getting another B after I drew the first B. So I have 15 B's out of 75 buttons for my first probability of getting a B. But now that I've taken that B out, I only have 14 B's left and 74 total buttons. So I times it by 14 over 74 because we've already selected that one. Multiplying those together, you can do that in Excel or on your calculator, which gives you 0.0378, or about 4 in 100. Now remember, that's for a dependent event, where one event is affecting the second. Let's go to jury selection. A jury of 3 members from a pool of 12, 6 men and 6 women. What is the probability of selecting an all-male jury? The probability of 3 men. So the probability will be the probability of a male times the probability of a male after the first male was selected, times the probability of getting a male after the first and second male are also selected. So the probability of getting a male from the very first draw, I have 6 men out of 12. So 6 out of 12. Now the next probability, I've already selected one of the men, and now the pool is down to 11. So I have 5 men left out of a pool of 11. So it's times by 5 out of 11. Now I want the third male, which will be timesing. I've already selected 2 men out now. Now I only have 4 men left, and now I only have 10 left in the pool. So it's times 4 out of 10. I get 6 out of 12 times 5 out of 11 times 4 out of 10, which gives me 120 out of 1,320, which gives us 0.091 or 9%. Moving to Roman numeral 2. When we see either or probabilities, this is adding. So remember, and means multiply, either or means add. And with the ands, we have independent and dependent. With the either or, we have non-overlapping or overlapping. I'd kind of write that out in maybe some notes somewhere so that you remember. And means multiply. And you look at either independent or dependent events. Either or, we have non-overlapping or overlapping, and that's adding. Non-overlapping events are when 2 events cannot occur at the same time, such as heads and tails. You either have one or the other. For either or probabilities, we have the probability of A or B. We just add probability of A plus the probability of B for the non-overlapping events. Let's roll a single die. What's the probability of rolling a 2 or a 3? So we have the probability of 2 add to the probability of rolling a 3. I guess we should probably write in rolling a 2 just to be a little bit more specific, rolling a 3. And the probability of rolling a 2, there's only 1 2 out of 6 sides, so it's 1 out of 6. And the probability of rolling a 3, I can't roll a 2 or a 3 at the same time, so they're separate, and I have 1 out of 6, which gives me 2 out of 6, which reduces to the probability of 1 out of 3, or 0.33 or 33%. Whichever one you want to write, because there's 3 different ways of writing a probability. You can write the fraction, the decimal, or the percent. Now, the next possibility for either or probabilities is overlapping events. This is when the 2 events can occur at the same time, such as drawing a queen or a heart. And it looks like this. So up here, we did a Venn diagram showing that these don't overlap. Down here, these 2 do, because I have one card that happens in both categories, the queen and the hearts. So if I want to find the probability of an overlapping event, A or B, I have to add A or B, the probability of A and the probability of B. But if I add the probability of getting a queen and the probability of getting a heart, this queen of hearts is added in twice. So we must subtract the overlap because she was added in twice. If I subtract it once, then I get the probability of all of them together. So I need to subtract the probability of A and B occurring at the same time. So let's find the probability of getting queens. I have 4 queens in a deck of cards, and I have 13 of every suit, so I have 13 hearts, but I have 1 queen of hearts, so I have to subtract that because she was added in twice. 4 plus 13 gives me 17 minus 1 gives me 16 out of 52 cards in a deck, or reduced to 4 out of 13. Let's move to another example, Democrats and women. In one room I have 8 people, 2 Democratic men, 2 Democratic women, 2 Republican men, and 2 Republican women. What is the probability that the person we select will be a woman or a Democrat? So I have woman or Democrat. The probability of a woman, well, let's come up here because I have my 2 things, women and Democrat. I have 2 women here and 2 women here, so I have the probability of 4 out of 8 for the women, and the probability of a Democrat, we have 2 and 2, so 4 Democrats, which gives me 4 out of 8 plus 4 out of 8. But I had 2 Democratic women, so they were added in the women and the Democrats, so I need to subtract one of them out, which gives me 6 out of 8, or 3/4. Note, if I were to have done the 4 out of 8 and 4 out of 8, I would have had 8 out of 8, and that doesn't make sense because I didn't count the Republican men. So I know something's up there. So if you have something like that, kind of double check and look back. Roman numeral 3, the at least once rule. The at least once rule, so let's look at it from this way. Let's see if I can have at least one head when I toss a coin 4 times. So if I'm looking at least once, the probability of at least one head in 4 tosses, that means I'm looking for 1 head, or 2 heads, or 3 heads, or 4 heads, and or means add. So I'm going to add all those together. So I have to find every single possibility and add the probabilities together. Or we could say that you do not get at least 1 head in 4 tosses is 100% of the tosses. So I either do or I don't get at least 1 head in 4 tosses, which we talked kind of like we did earlier. This is the probability of at least 1 head in 4 tosses plus the probability of no head in 4 tosses, which equals 1. So again, if I subtract the probability of no heads in 4 tosses, I get the probability of at least 1 head in 4 tosses equals 1 minus the probability of no heads in 4 tosses. Now let's talk about the probability of no heads in 4 tosses. That means I toss it once, twice, 3, 4 times, and the probability of not getting a head is 1 out of 2, 1 out of 2, 1 out of 2, 1 out of 2, which equals 1/2 to the 4th power. So I can replace that up here, and the probability of at least 1 head in 4 tosses is 1 minus, this is 1 out of 16, which gives me 15 out of 16. And that leads us to our rule, the at least once rule. The probability of at least one event A in n trials equals 1 minus the probability of not getting the event A in 1 trial raised to the n number of trials. So if I have a 100-year flood, all right, let's move to the next example. A 100-year flood. The probability that the 100-year flood will be experienced at least once in 100-year flood, or 0.01, because it's 1 out of 100 during the next 100 years. So we're going to do the probability of at least 1 flood in 100 years. That means I have n is 100 because I have n trials. The probability of at least 1 flood. Now I want the probability of not 1 flood because it's the probability of not A in 1 trial. So the probability of not a flood in 1 year, we take the opposite, or 100 minus 1 minus the 0.01 gives me 0.99. That's the not part. Now I need to raise it to the n number of trials, or 100 years. So I have 1 minus 0.99 raised to 100, and I can do this in Microsoft Excel if you want. I'm going to go ahead and copy. Oh, I don't have it open. You would copy and paste it in, and if it doesn't show, you would do a caret here when you calculate that in Excel, and it will give you 0.634. All right, let's move to the next example. 10 lottery tickets. So you buy 10 lottery tickets. What is the probability of winning on 1 ticket? Oh, the probability of winning on 1 ticket is 1 out of 10. So each ticket has a probability of winning of 1 out of 10. What is the probability that you will have at least 1 winning ticket among the 10 tickets? So I need to define what n is first. So n trials, I have 10 tickets. Now I need to find the probability of not winning in 1 trial. Well, I know the probability of winning in of winning is 1 out of 10. So not winning, remember to find not is 100 or 1 minus the probability of it, which in this case is 0.9. So then I plug it all in. The probability of winning at least one winning ticket in 10 tickets is 1 minus, just like the equation, 1 minus the probability of not winning, which we found is 0.9, raised to the number of trials, which I have 10 tickets, gives me 0.651. Let's move to Chevalier, which you talked about at the very beginning of the chapter because you read the section before watching the video. He bet that he could get at least 1 6 within 4 rolls of a die. Let's find the probability. At least 1 6 in 4 rolls. So I need 1 minus the probability of not rolling a 6 in 1 roll raised to 4, because that's the number of trials. So I need to first find the probability of not rolling a 6. So rolling a 6 happens 1 out of 6 times, so not rolling a 6 would be 1 minus that, or you could just count that there are 5 other options to not getting a 6. So I have 1 minus 5 out of 6 raised to 4 trials. Again, you can use your calculator or Excel and get 0.518. He had originally guessed that it was 4 out of 6, which is 0.6667 or 0.67, it just wherever you round it. Now he guessed a lot higher. Now it's not quite as high, but it is still above the 50% mark, so he would end up winning more games than losing, but he would have to play a large number of games, which we will end up getting into when we talk about the law of large numbers. In his second game, he bet that he could roll double 6s within 24 rolls. So let's go ahead and figure that one out. So double 6s, that means a 6 and a 6, and that's an and, so I need to multiply. So 1 out of 6 times 1 out of 6 is 1 out of 36 double 6s. So not getting double 6s is 1 minus 1 out of 36, which is 35 out of 36. And we know that because of our chart that we drew earlier in 7a and at the very beginning. And there are 35 possibilities of not getting that double 6. So now we know the second part of the equation, this part, the not in 1 trial. So we need 1 minus the probability, we already found the not rolling double 6s, raising it to the n number of trials, which is 24, 1 minus 35 over 36 to the 24. Plugging that in your calculator or Excel will get us 0.49. Again, this is just a little under 50, but even if he plays a lot of games, he's going to end up losing slightly more times than winning. And so this was the better of the two versus this one. And that kind of moves us into the law of large numbers. I hope you join me with 7b or 7c.